Okay, so thanks for coming to the first session of the day on the first day. So it's good to see everybody. We want to talk a little bit about some of the things around live migration and why it's necessary, and specifically Mike will delve deep into the host management of NVMe Express live exported NVM Subsystems. So with that, where's my page down? There we are. So I think everybody knows me. I'm Lee Prewitt. I'm a Director of Hardware Cloud Storage at Microsoft. And I'm also the Microsoft board rep for NVMe, and as well as the co-chair of the OCP storage track. So kind of a hyperscaler perspective here. And some of the challenges around if you're going to do live migrations, what are some of the things that you need to be able to prove to the guest? It needs to be consistent, predictable, performant. There shouldn't be big dropouts in time for the VM. You need to be able to keep them working efficiently because that's what they're paying you for. The historical approach kind of achieves these goals. A lot of it's the fact that we ended up doing lots of para-virtualization, and we'll talk about that more later. But it's that works against things like latency, and it works against things like sellable CPUs. So the way to standard solve this challenge much more durably. We've been working on this with Samsung and Google for a while now, working through some of the pieces, putting them together in different TPARs and TPs and within NVMe. And we've been able to solve a lot of the challenges, but there's, again, always some more stuff to do. So we can now at least start to be putting together some of the pieces and start to test some of this stuff at scale. So why do live migration in the first place? Well, customers hate to be interrupted while they're working. As part of this, one of the things that is a very important metric for us at Microsoft in the Azure is what we call annual interruption rate. You need to have that be very, very low, otherwise you get lots of angry calls and emails to support and that sort of thing. So live migration is something that we were using to try and meet those AIR goals. And what are some of the cases for that? Obviously, we have imperfect hardware, and the problem is that sometimes something on the node will fail. And so we're going to have to take that node offline so that we can get that hardware repaired. And sometimes, if we're lucky, that piece of hardware that failed didn't interrupt the VMs, or it only interrupted a portion of the VMs that were running on that machine. Say it was an SSD that took down several of the VMs, but not all of them. So then we'll move those other VMs off, and then we can do what's called OFR, out for repair, and get that piece of hardware replaced and get that node back in service. Another one now where obviously we have to have some AI buzzwords in here. We've got a lot of machine learning going on these days that starts to do predictive failure for some of the components. And so if we get that predictive failure signal, we can now live migrate everybody off and then take things out to do things like, say if the SSD looked like it was misbehaving, we can do things like format the namespace and do some other resilvering ideas for that, and then bring that node back online again. Another one, scheduled node maintenance, right? When things need updating, maybe you need to put in some more DRAM, maybe you need to update firmware that isn't being able to done seamlessly online, and that sort of thing. So we need to move stuff off and do that sort of thing. And finally, one of the big ones is load balancing. So if we have a node that's got lots of small VMs on it, and we need to find a place for somebody's really big VM, we may want to live migrate some of those smaller VMs off to give us a spot for a big VM. As well as things like if there's a series of VMs that are running very hot, and we want to try and cool that node down by putting some of the heavier use VMs on another node that's less or more lightly loaded. So why is para-virtualization not enough? This is kind of the way it has always been done in the past. You have virtualized hardware through a hypervisor. But the problem with that, SSDs are fast, and para-virtualization is slow. You've got a lot of software overhead that then starts to burn things up. And for us, para-virtualization is also expensive. Because if we have to have a CPU core or two running the hypervisor, that's a sellable core that we lost to try to get money from a customer. So first thing we did here is get the hypervisor mostly out of the path. So it's the 4165, that's the LBA tracking TP. Then we have 4159 for the PCI infrastructure, all the namespace migration, the controller migration, and all that. So kind of all of the data and the state. And along with that, what we're working on now is quality of service, such that you can, given a piece of a somehow virtualized piece of an SSD, how do you ensure that the VM only gets the IOPS and bandwidth that it paid for? So that's what we're working on now. But it's all good, but not quite enough. One of the things we need to do is actually get out of trapping the admin queue. I mean, it's not CPU intensive, but what we want to try and do is minimize the hypervisor attack surface. And this plays into confidential compute going forward. But what we have to do, once we've taken the hypervisor out of this, we can no longer have it lie on our behalf about what the VM sees. So that's where the PCIe Exported Subsystem comes in. It's how to tell a consistent lie across different devices. What that does is it's a way of abstracting all of the stuff that would be controller specific. So, it has a Samsung part number in it, and it's got a Micron serial number, and, all these other things. And we have to kind of abstract that out, say what we're going to have the device tell each VM on our behalf. And then when we live migrate that VM, we're going to tell them wherever the destination is to tell the same lies. And it abstracts out all the command support and stuff like that. So, are we there yet? Well, not quite. Still need a couple of pieces left. One of the things that I'm working on, trying to move forward, is the standard way of allowing the SSDs to be parceled up. So you can think of this as maybe the device has multiple physical functions. So how do you give all out the physical function resource? What's the namespace? How big is that namespace? How's it attached? That sort of thing. But that could be either physical functions, SRIOV functions, or even SIOV namespace, signable interfaces, that sort of thing. And then one of the final pieces, as we again talking about confidential compute, is TDIS support for NVMe. So we now are working on something where we can standardize the device interface report that a confidential VM would get back through the TDIS mechanisms when they want to lock down the interface. So with that, Tanya's going to go through this in a little more depth.
Hello. Thank you, Lee, for a very nice introduction about the basics of live migration. I'm planning to dive a little bit deeper into live migration process, some of the steps that happen when you actually start a live migration, and cover how the standardization is going to benefit for us to have upstream Linux kernel support for this particular TP. So a typical live migration scenario includes these 5 steps: pre-migration, reservation, iterative pre-copy, stop and copy phase, and commitment. So when you initiate a migration, your hypervisor or migration software or orchestration agent will go through these roughly 4 or 5 steps. They may differ platform to platform. So what happens in pre-migration, you have 2 hosts. One is source and the other is destination. And you have an active VM that is running. So you initiate a pre-migration state and make sure you have the right host accessible and associated with the migrating VM, that is the VMA. In the reservation phase, you end up allocating the resources and making sure you have all the necessary capabilities that you need for VM to be migrated, and all the features that you have assigned to the VMA, they are available on the compute node for VMA. So that's the reservation phase. The next phase is the iterative copy. So obviously, when you have larger VMs, your memory footprint is going to be very, very large, depending on how your pages are laid out in the memory. So how do you actually deal with this problem? So you start iterative copy, and your finite state machine is probably going to have a pre-copy phase where you start shipping these pages which are not accessible or which are ready to be shipped and not part of active working set. In this phase, it allows you to optimize VM downtime, which is the next phase. So this is a split brain phase where your VM at the source is stopped, and you have partial state that is divided into source and the destination. And in this phase, you ship whatever the remaining delta is from the iterative pre-copy, which must be very, very small, to the compute node, and finish all the resource assignment subsystems, making them live, or any other stuff you want to do. And the final phase is commitment, where you start the VM on the destination side, and you do all the cleanup that is needed to be done on the source side. So these are just 5 different, very simplistic steps. Any questions? Okay, can move forward. So NVIDIA published a research paper in July 2022, and we presented why NVMe standardization is needed. And that research paper has the architecture for live migration commands. How can you do dirty page tracking? What kind of optimizations you can do in iterative pre-copy? And we evaluated many different nodes, different types of modes that you can use when you're using NVMe SSD with upstream QEMU, VFIO, live migration infrastructure. So there are quite a few modes you can use your SSD when you are using QEMU, and there are like 6, 7, 8 modes, and there are sub options you can use. So on top level, you have about VFIO backend, then you have NVMe user space backend, then you have generic block device backend, and file backend, where device is formatted with a file system, and then you have a file that you assign it to VM. So these are the different weights you can use. So what is the most optimized way for NVMe SSD to be used with virtual machine? That is VFIO backend. And we'll go to the performance numbers soon, but just keeping that in mind. So what is the VFIO mode? So VFIO mode is a virtual function mode where virtual machine just turns into a user space application and access device into pretty straightforward protocol agnostic mode, and you can use virtual functions out of physical functions and assign those virtual functions to the physical functions and use that for live migration. So application, particularly in high performance computing field, they benefit from very low overhead and direct access from user space. And some of these examples are TCP/IP based compute accelerators, and most of the high performance devices or interfaces, they use VFIO for the performance benefit that you get as compared to rest of the modes that you have. Let's skip that. So these are the performance numbers that we collected. On the very left side, that's the pass-through mode, that is the VFIO mode. And on the extreme right side, that's the native mode, that is a raw NVMe SSD. And you can clearly see that And in between, there are like bunch of different modes like block mode, NVMe user space mode, and XFS-based file caching mode and whatnot. So you can definitely see that in terms of performance, VFIO mode is clearly superior mode than any other mode to be used with NVMe SSD. Now, when you're using VFIO mode, VFIO has an infrastructure. It's called finite state machine, where it allows you to plug in your own set of drivers for your own protocol that can be used in QEMU live migration stack. So what we did in the NVMe specification is we defined commands. Those commands will be called from VFIO live migration framework from the finite state machine, and those commands will get executed on the NVMe controller, and the entire 5-step process that I just explained earlier will get executed. And these are just more performance numbers to justify. So that's why we need a live migration support in NVMe, so we can have NVMe VFIO driver that is standard compliant and can be used with native Linux support. So in 2022, NVIDIA and Intel submitted non-standardized Linux kernel code that is a part of online discussion. This year, and last month, I submitted second version that is partially based on the 4159 TP, and right now I'm in the process of working through some of the details and submitting the next version so we can have native Linux support. Thank you.
Hello, I'm Mike Allison. I work for Samsung. I am leading some of the editing efforts that's going on to all those TPs you heard about, and the TP I'm here to talk about, which is the PCIe Exported NVM Subsystems. So with that, since NVMe 2.1, there was this new entity called an Exported NVM Subsystem, which was created for NVMe over fabrics. The intent of that was to take a large storage system and allow it to be broken up into subcomponents so they could be managed well. When I see exported NVM subsystems, I think of virtualized SSD, but I'll use the NVMe term there. What's different now for PCIe that we didn't have in NVMe over fabrics is now we're adding this thing called an exported controller. In NVMe over fabrics, they have an exported port, and when you connect to the port, you get a controller. So they didn't have this term exported controller. And so what we're trying to do in this TP is a host is still going to connect to what we're calling the underlying controller. You're still going to use the same physical controller. But now we're going to virtualize, and we're going to create this exported controller. And we're still going to use the exported namespaces that was defined in what came out in NVMe 2.1. And what really happens now is this host, or the VM that they've been talking about, while he's really interfacing to this underlying controller, what he's going to see is this exported NVM subsystem and its state, which could be different than the underlying NVM subsystem of where it exists. But he's going to see these IDs for the controllers and namespaces. He cannot see any other resources that are outside that boundary. So it provides isolation. And what more is the host, the orchestrating host that sets this up, gets to select what these numbers are. So now we have a virtualized environment for the entity numbering. And the orchestrating host gets to do that. And now it doesn't matter what the underlying resources are or what those numbers are. And the underlying resources, the numbering, is actually picked by the controllers themselves. So what's important is those two numbers, okay? The other thing we're doing is when we look at an exported subsystem, we want to be able to define a template. And a template is something that says, hey, here's you export a controller, you're this template. But that template can define what that exported NVM subsystem supports. It can define what log pages are supported, what commands are supported, what features are supported, what default values of features are supported, just by the template itself, with no API other than the template ID. The other thing that can happen is we're going to allow that template to define programmable features that go along with that template. It's going to define the data format, and what variables. So for example, maybe MDTS. You can have a range of what MDTSs you want to support. So as we think about migration, then this is where migration gets involved, because if you're going to migrate from one SSD to another SSD, that they may not be the same company. They may be the same company, but different families of SSDs. So what's important there is, at this point, if you're going to migrate, we need the host to manage all of the unique identifiers as well. You have unique identifiers for the NVM subsystem, you have unique identifiers for the namespaces, and we want that orchestrating host to define all of those, so when you move from system to system, those unique IDs go. But why is it so important? Well, when you have a unique ID, as an SSD vendor for Samsung, I say, here's my unique ID. I'm in control of it because I give it to you, host. But if the host gives it to, in the world, somebody else to use, I've lost control. But if the host defines it, they own the control. They can guarantee that that unique ID is consistent in their environment, such that there's only one that exists at any given time. Then it comes into migration. And what's important for migration is the fact that I have these exported entities with these numbers that I can build somewhere else when I'm doing the migration, and I get to define this configuration as well. The other thing about this template is a particular SSD says, I support these templates. And if they support the templates, they support everything that's defined by that template, all of the features, all of the log pages, and everything else. What's really interesting is that template here can say, oh, I support these log pages or whatever, but it doesn't mean that this underlying system, the underlying controller, can report different things that it supports. It doesn't have to be the same. So as an SSD vendor, I can build what I need for my customers and test what I need for my customers in the given situation. I don't have to expand my list to try to do everything. I can just keep it focused, because one of the things about building SSDs or any peripheral, a lot of testing. And if we can keep that scope down, it helps minimize effort and resources and cost and everything else. So the only way I can know how to do this without using a lot of words and confusing everything is I like to use pictures. And we're going to do a migration, okay? We're going to take this orange VM connected to the exported NVM Subsystem X and move it over here. One thing that we're going to do is we have this X number here for the exported subsystem. This X is only relative to this underlying source system here. It's unique relative to this. It's not unique across the whole world or anything else. So an underlying namespace and an underlying controller, that's your real physical controller, and that's your real namespace. If you do a create namespace in NVMe today, that's the namespace you get it. We're just calling it the underlying namespace. And this controller here can be any type of controller. It could be a physical controller, a VF controller, maybe SIOV if they ever bring those in. It doesn't matter what controller type it is. So to migrate over here to this destination, there's already an underlying exported, there is an export NVM subsystem already that exists there, and I have one free controller over there that's not being used. This is a simplified version just to make it to go through the presentation. So the first thing that has to happen is, if we're going to migrate from the source to the destination, he has to create an export subsystem over there. And he's going to get an identifier for this, but again, that identifier is related to the destination underlying name system. That's just so the orchestrating host can say, I'm talking to this exported NVM subsystem and this underlying NVM subsystem. Now, over here in the VM that we're migrating, he has exported namespace 1. And he needs to have that same thing. But what he doesn't have is he needs to take this namespace and get it over here. And in NVMe, when you create a namespace, the controller picks that namespace in the underlying controller. Host cannot control that. So what we're going to do is when he creates a namespace in the destination, It doesn't matter what the underlying namespace is. It's the orchestrating host's responsibility to take the data in here and migrate it over here. And I'm not going to cover that today because that was done in TP 4159 on how to migrate a namespace live. All right? So he can create this underlying namespace and start migrating the data over there. In the meantime now, because he understands that he wants to have the same numbers back and forth, there will be a command that says, create me an exported namespace and associate it to the thing that in the underlying namespace that I created. Now when you look at the controller, I need exported controller in the destination of 0. I'm using the physical underlying controller 1 over there, but I don't have 1 on the other side. So we're going to have a command that says pick any of the underlying controllers and call it the exported controller of the number of my choosing. So now as you can see, I have an exported namespace Z in the destination that has the exact same exported coordinates as I do on the source. I'm still not done though. I still need to set up the configuration data that we talked about with the template. So in the destination, you can program that configuration to be exactly the same. Hey, you're this template, here's your data, the programmable data. And now the fundamental base capabilities of this is now ready to go for migration. Now the next step comes in TP 4159, we can get to a point where I'm ready to migrate the final state in which I can pause all the processing on the...
Just say pause. Check your power cord.
No, it's there. I lost it. Are you lost up there, or is it? It's between there and here. It's fine from me to him. This happened right before the presentation. We're a little ahead of time, so we're okay. All right. It always happens. It always happens. All right. So what happens this for my migration now, we can get to a point where we pause all of this here to say stop processing. Now this pausing and resumption is already done in TP 4159. I'm not going to repeat it here, but what I do want to talk about is this migration data. This migration data is the data that is defined by the template, and it is for the entire exported NVM subsystem. In TP 4159, when we did controller migration, we did controller state. We didn't have namespace state. We didn't have NVM subsystem state. We didn't have feature state. We didn't have log page state, and that's what we're encompassing here. So this template is going to define what's in the migration data. And the other thing is, as they all pointed out, is when we're doing this final migration of the final data, you want to pause, move the data over as fast as you can and get up so your downtime is low. The other thing that I'm not covering here is this migration data can also be carried over live. If it's a large set of data, if you're emulating your exported NVM subsystems, it could be a large set of data. You're free to do this live, but I'm just showing you the dead time. So there will be a command for the orchestrating host there to say, go get the data and bring it to me. Now I have this final set of migratable data, and then he is responsible for transferring it over to the orchestrating host on the destination, and then there will be a command that says, all right, take the current last state that you had while he was paused and put him in the controller. And then it's up to the orchestrating host to actually move the VM itself, which could be done live using the same steps that was done in the previous definition. So now, as you can see now, everything is here. You can unpause the processing. Everything got moved over, and now he's running. And this host still think he's talking to exported controller 0 and exported namespace 1. He doesn't see any of the hardware changes that have occurred because this configuration data is doing the lie that you talked about. All this is done by the host. So now what happens is this host can now talk to this underlying controller, which is being reported as controller 0, and he can actually talk to the admin queue live. There's no trapping of data in the hypervisor or at all. So it's all done inside the SSD itself. The final step would be now is to go and delete all of those exported entities in the source, and then you can delete the namespace, and now you've done a complete migration. Okay. The real important part is the fact that we get to control the numbers here, and we get to do this. Now, one of the things that we're thinking about is this new template can also be applied to NVMe over fabrics. They can do that there. They didn't do it before. They were going to just break it up. You use the underlying resources, whatever they report, but now they can take advantage of that in NVMe over fabrics. The TP that we're focusing on is really on PCIe. We're not trying to change NVMe over fabrics, but if you're working on NVMe over fabrics, it does allow you to say, hey, I can go create something over there and I can control what it wants to support for my needs and limit things. So with that is the end of our presentation. Any questions for any of us? Yes?
Just finishing on your last thought there. So are you proposing that there could be a solution to migrate from a PCIe to an NVMe over fabric namespace?
I haven't thought about that. He's asking, have we thought about migrating from PCIe over to an NVMe over fabrics? And back. I guess you could tentatively do that, but one uses ports and stuff and the others, but the underlying NVM part of it, you can. The good news is the template is a unique ID which can be defined by NVMe or vendor specific. So on the vendor specific side, if you wanted to create your own template that would allow you to do that, you're free to do that. You would just have to define all the pieces. If you define your own, we're going to use UUIDs for the template. If you define your own, that means you have to define what it supports in terms of log pages. You'll have to define the programmable data, and you'll have to define what the state is. And if you wanted to go back and forth, that's probably something you can do, but I hadn't entertained that thought at all. I'm a SSD guy, so.
It uses dynamic controller model, and PCIe, it doesn't use dynamic controller
Correct.
model. So how we are going to even align those controller creations if you want to go from PCIe to fabrics, fabrics to PCIe? It's a fundamental issue with the design.
But it's programmable. You can do whatever you want, I guess. Yes, sir.
I had a question for Chuck. I should have asked this earlier. I noticed that in some of your foils they were dated 2015. Next time you do that, I know the block diagram really goes back more than a decade, but use that to call out how things have changed, but how they remain the same.
That's the whole purpose. Even in today, 2025, the basic concepts of line migration still the same. There is no fundamental difference in those 4 or 5 steps you would want to do. That just streamlines the entire process, and that also allows us to do standardization. And within the finite state machines, that we can take an advantage of standard commands. As NVIDIA, we have submitted more than 200 patches to rewrite the finite state machine of VFI line migration. And we have many different drivers. They actually take advantage of that particular finite state machine for VFI. So now we just want to look for.
And then one other thing I didn't mention in my presentation is when you create the exported NVM subsystem, we are not limited to just one exported controller or one exported namespace. It could be one or more, okay? I just showed a very simplistic view of here just to make the pictures work very well, but it's really dynamic, okay?
So that 2 above and below could be,
I could create one with four controllers, right, and 4 namespaces, or however you'd like to do it, okay? Yes, Paul.
Could you go back to the picture of the subsystems? So if I understood correctly, the orchestrating host on the destination system, when it assigns all the various identifiers to the exported controller, it'll choose those from the space owned by the underlying NVM subsystem.
Yes, yes. So what he's asking is the orchestrating host in the destination, when he's trying to carve out the resources for the migrating exported NVM subsystem, he would go through his list of available controllers that are allowed to be used under this, called an underlying controller. He gets to pick the physical underlying controller to use, and it doesn't matter. because it could be any of the controllers, because you're lying to the VM when he comes around. But he gets to assign the exported controller number. So that way the VM, he thinks he's talking to exported controller 0 in this case. He's not going to see the change in the underlying hardware. All right, and getting back to unique IDs, you know, if you're migrating from a Samsung to another company's there, you don't want to all of a sudden say, oh, I was Samsung, now it's another one. Or if you did that, you know, I don't want another company to say I'm Samsung when I'm not either as well. Did you have a follow-on with that, Paul?
Nope, just wanted
Okay.
to clarify that first.
All right. And just understand that what we're trying to do in NVMe is we're giving services to the orchestrating host to do what he needs. And he's telling us what to do and giving him the API to manage all those commands. The orchestrating hosts here need to coordinate on that and understanding what they need. So here, from an SSD point of view, all my concern is I'm going to allow you to create an exported NVM subsystem. I'm going to allow you to assign exported controllers. I'm going to allow you to assign exported namespaces. How you manage them and what you do is up to the orchestrating host.
So that becomes a part of reservation phase that I explained in those 5 steps. This is what you do in the reservation phase and make sure you have all the resources are reserved on the destination side. And then you continue the line.
Yep. All right. Any other questions? Yes.
And the designation and construction of that template is now in a TP phase?
Well, the TP is, I don't know if you know about NVMe, there's phase 1, phase 2, and phase 3. Phase 2 is theory of operation, understanding all the commands, whatever. So right now we're in phase 2, the later stages of phase 2, right now. As far as the template, we plan to identify one template, okay, and go over all the pieces. But I have a feeling that in dealing with everybody in the ecosystem, they all have their own unique data that they need to migrate for various things. So my expectation is NVMe is going to give you the commands to specify a template, but if you use a vendor-specific template, you define that data, and it won't be in the NVMe spec. It'll be in some other spec. And I expect over time, we may add more to NVMe, and I think we'll have a mixture of customers saying, here's my template, here's what you're going to do. You may have other organizations that define templates who maybe they'll even do one in SNIA, I don't know.
Linux versus Twitter competition.
Well, you have different things. I mean, you have a PCIe SSD that's physical, all this stuff is physical stuff. And you could have emulated NVMe stuff that I have a real CPU running down there and I have to migrate it. It looks just like a VM and I have to migrate that. Those are two different, completely different things, right? Because with you have a physical thing, all I care about is what are your properties, what are the state of all the things that the host can see, and I migrate that and I create it on the other side. But if I'm doing a CPU and I'm migrating the CPU components, I got to treat it just like memory and all that other stuff and migrate that. They're totally two different things. We did look at trying to make it really generic. You can do all the stuff you want, and it just got too complicated. And it's just way too complicated. Maybe we need that in the future, but we felt doing the template now would give us the ability to have the API that we need. Okay? Good question. By the way, come to NVMe. We're talking about it every week. So if you care, you have your inputs, please come, because everybody else is giving me their inputs. It's a really fun TP actually to work on. And she's telling me we have 10 minutes, but we're done now already. Any other questions? All right, thank you.